Okay, so we are ready to start. So this morning we have Manav, Babel from STFC, UKRI. So Manav, take it away, please.
So yeah, hi everyone. Thanks for coming along to the talk and I hope you find it interesting. I'll be presenting on the work that's been done in a feasibility study that's been carried out by us at the NQCC with Unisys and Newcastle University on aircraft loading. So first I'll give you all a little introduction into the NQCC and what we do. And then I'll discuss the aircraft loading problem and why it's important before moving on to how we chose to solve it. I'll talk about the experiment we ran, comparing different methods and the results, followed by some key improvements we made, including improvement in the embedding algorithm, which reduced the time taken to embed something from 20 minutes to under a second. And finally, I'll talk about the upcoming experiment, what we have planned, and what we hope to get from it. So first up, the NQCC. The National Quantum Computing Centre, or NQCC, is the UK's national lab for quantum computing. We were created about 5 years ago with the mission of working with businesses, government, and the research community to get quantum computing capabilities for the UK. To do this, we focus on 3 key areas, which are technology development by building and testing quantum computers in a range of modalities in-house, quantum readiness by encouraging, assisting, and collaborating with organizations across a huge range of sectors, and in establishing a cutting-edge infrastructure by investing in equipment, facilities, and talent, notably via a test bed call, which closed a few months ago, where we agreed to procure quantum computers from a number of hardware providers to be hosted in our new state-of-the-art facility in Oxfordshire. So if you'd like to find out more or are interested in collaborating, please visit our website or drop us an email. And with that, onto the problem we investigated. According to the World Trade Organization, every year air freight accounts for 35% of total cargo value transported, which is about $18.6 billion daily. It's a huge sector, vital to the transport of delicate or time-sensitive goods, while also having thin margins and accounting for about 2% of global carbon emissions. And as such, any efficiencies that can be made can have an outsized beneficial impact on both the companies involved and the wider community. One area where efficiency can be made is in cargo loading and arrangement. Cargo is loaded in unit load devices, or ULDs, which you can see here, picture on the right, to ensure standardization and ease of transport. And the placement of these ULDs in the cargo bay is extremely important and can have serious effects. A displacement from the optimal position of just 75 centimeters over a flight from London to Tokyo, for example, wastes an additional 4,000 kilos of fuel. And in extreme cases, takeoff and landing can become very dangerous if operational tolerances are breached. However, the problem of selecting and arranging these ULDs is extremely difficult and time-consuming to solve classically, meaning that currently it's performed manually by load planners who use a combination of experience and intuition to load the planes, which often results in delays and suboptimal solutions. This feasibility study was therefore performed to assess whether quantum computing can help with this problem, which can be expressed as this statement. Given a pool of ULDs, pick the highest value subset and arrange them in the cargo bay such that the center of gravity is as close to the optimum position as possible. Specifically, there are 3 questions we wanted to answer. Firstly, can this problem be reformulated as an optimization problem for quantum computers? Secondly, can current quantum computers solve this problem? And finally, are these solutions better than the classical ones, being either more optimal or faster? In preliminary testing, we found that for problems of the size that we wanted to solve, with tens to hundreds of ULDs, current gate-based computers simply don't have enough qubits to solve them. As a result, we had to use D-based quantum annealers. To solve this problem, we split it into 2 parts. The first phase was to solve the knapsack problem, taking the ULDs with the highest value, for which we used weight as a proxy. We assumed the ULDs came in one of 3 sizes, which is a half, single, or double. And then if xi is the binary variable for whether ULD_i is taken, the objective is simply to maximize the mass taken, while ensuring that the total weight and total mass don't breach the limits. Phase 2 was the actual center of gravity optimization problem. We assumed that we had a single cargo bay and had to arrange the ULDs to ensure that the center of gravity was as close to the center as possible. So we defined xij as the binary variables for whether ULD_i is placed in slot j. And then the objective becomes to minimize the total moments around the center of the plane, which is represented by the first 3 terms in the sum. This last term in square brackets is essentially a delta function. It just stops us double counting the two ULDs. For physical realism, we also had to include 3 constraint families to ensure that every bay had at most 1 or 2 ULDs, that size 2 ULDs were in consecutive bays, and so on. From this formulation, we implemented a couple of classical solvers to provide benchmarks for the quantum solutions. For an exact solver, we used the Python package with the ship solver, which we chose because it can solve non-convex objectives, like a complicated class games. We also made a couple of greedy solvers, which used heuristics. For phase 1, which was simply adding ULDs in the order of density until one of the constraints was breached. For phase 2, the heuristic we used was adding ULDs to each end of the cargo bay according to the Thue-Morse sequence, which is known to be the fairest way to split a pile of goods. After implementing these classical solvers, we considered annealing. This was harder because first, to solve the problem using annealing, we have to change the problem. The phase 2 objective included an absolute function which can't be handled by the QPUs, which is why we had to switch it with squaring the entire objective function, which of course drastically increased the size and complexity of the problem. QPUs can also not handle constraints, which is why we had to convert the problem to QBOs, or quadratic unconstrained binary optimization problems. The first step was to convert the constraints, which were inequalities, to equalities, which was done by using slack variables. Essentially, we take the scalar on the right-hand side and expand it as a binary sum, and then assign slack variables to each of the terms. So every value in the original equality can be represented by some combination of these binary slack variables, which of course introduces a significant number of extra variables. Then we need to include these constraints in the objective via the Lagrangian method. This involves rewriting the constraint as a term, squaring, and adding to the objective itself. For example, here, the constraint ax equals b becomes the term lambda times ax minus b, all squared. The rationale here is that infeasible solutions will cause the penalty term, which is this term here, to be non-zero, which penalizes the solution. The value of the penalty is determined by this coefficient here, lambda, which is known as the penalty coefficient. And determining this lambda is quite a difficult problem. If it's too small, infeasible solutions won't be penalized enough, while if it's too big, it will distort the cost landscape, and the optimizer won't be able to find the global minimum. We decided that the best method was one published last year by Alessandroni, which involves efficiently calculating an approximately good solution. Finally, in order to solve the problem with annealers, we have to embed it, which refers to finding a mapping from the problem graph to the QPU graph. The problem graph is what you get if you assign all the logical variables nodes and add edges if the variables occur in the same term in the objective function. For example, here, if the objective had a term 6.5 x3 x4, then the x3 and x4 nodes would have an edge between them. The QPU graph refers to which qubits can be coupled. We use the D-Wave Advantage System 6.4, which has around 5,600 qubits, and the Pegasus V16 graph, of which a subset is shown here. Since in general, the problem and QPU graphs won't be isomorphic, the embedding has to find a mapping, often daisy chaining physical qubits together to exploit their collective couplings. After the reformulation and embedding, which could be performed by the minor package from D-Wave, we send the problems off to be solved. However, we encounter a problem which was that our QUBO had a huge dynamic range, meaning that the largest terms were orders of magnitude larger than the smallest ones. So this meant when the coefficients were scaled down into the QPU's bias and coupling field strengths, the smallest ones fell below the noise threshold, meaning that they were significantly affected by noise. This, of course, degrades solution quality and often returns infeasible solution. The only potential mitigation we could find for this was reformulating the entire problem, which we're currently exploring. I'm sure you're all familiar, but annealing involves slowly transitioning from an initial mixing Hamiltonian to a problem Hamiltonian, controlled by the anneal fraction, which we label S. We also wanted to explore reverse annealing, which is where you initialize the anneal with some solution, move backwards for a bit, and then resume forward annealing, which has the advantage of planting you in the feasible subspace, making it more likely you get an optimal feasible solution. We identified 2 annealing schedules we wanted to test, which was a short symmetric one of just 20 microseconds, and a longer asymmetric one with a pause at 60 or 20 microseconds. These were chosen after a literature review, but of course there is scope for more detailed exploration of the effects of different annealing schedules. Once this was all set up, we ran an experiment comparing the classical methods, which were run on an HPC system, with annealing and several variations of annealing run on the Advantage 6.4. We generated problems with these cargo bay sizes, tested them 50 times each, and solved them with that range of methods. The results I'm about to show are preliminary. We're currently working on a more detailed analysis, which we've pre-registered, but that hasn't been completed yet. This graph shows the results of phase 1. The x-axis is the problem size, and the y-axis is the weight ratio, which shows how much of the available capacity a given solution used. You can see that while orange and blue, which were the classical solutions, are consistently around 1, which is the optimal, the red and green, which is annealing and reverse annealing, are much worse. Reverse annealing is closer, but since it starts off with the greedy solution, it seems like annealing has just made the solution worse. Not only is the quality bad, this second graph shows that for larger problems, most of the anneals are actually failing to return any feasible anneal. So for each problem and method, we perform 200 sweeps of annealing and pick the best one. And this y-axis shows what fraction of those is a feasible solution at all. And you can see it very quickly drops off to something like 0 or very close to it. We can also look at solver time, which is the time between sending off the problem and getting a result. But all of the times are pretty similar for phase 1. The difference comes when we examine embedding time. You can see that embedding is actually vastly slower. So in terms of problem size, embedding time quickly ramps up to several minutes, which of course would dominate the actual solution time. So overall, it seems that annealing is pretty poorly suited for phase 1, with classical methods returning better solutions faster. For phase 2, it's a slightly different story, where phase 2 was the ULD arrangement. The solution quality is much more comparable. The y-axis here is the position of the center of gravity divided by the length of the cargo bay, and 0 is the optimal. And you can see that reverse annealing in green matches the classical methods for smaller problems. However, both annealing methods fail for larger problems, with annealing failing very quickly and reverse annealing failing a bit later. This actually isn't directly a problem with the annealing, but with the embedding. The red line on this graph shows what fraction of the problems a feasible embedding could be found. And so while for small problems, all of the problems could be embedded, for large problems it very quickly drops off, with no embeddings found for problems of size 20 or 27. Furthermore, the blue line shows how long the embeddings took, which reaches up to 20 minutes for the larger problem on an HPC system. The problem on the left shows the solver time as before. Here, Pyomo is again the solverist, but this time it displays a very significant scaling, while annealing is actually much better, being linear. So overall, we see that for phase 1, the knapsack problem, classical methods seem to be better and faster than annealing. Phase 2, embedding is a problem, taking an extremely long time and failing very often for large problems. However, if we look at the solver time and solution quality, it seems that annealing may scale in time much better than classical methods while providing good solutions. And so the immediate next step for us was to solve the embedding problem, which we started working on. First improvement we made was the problem reformulation to reduce the problem size and connectivity. We did this initially by redividing our variables. For example, we were using 2 variables to encode the size T ULD, plus an entire family of constraints to ensure that the ULD wasn't across bays that weren't next to each other. Instead, we could represent size T ULDs with just one logical variable, which reduces the number of variables and also removes that entire family of constraints. Another improvement we made was to switch our encoding scheme. Initially, we were using one-hot constraints, which meant that, for example, of all the variables representing a certain ULD, only one could be 1, and the rest had to be 0, which was enforced by a set of constraints. We can instead switch to a domain wall encoding scheme, where the position of the ULD is defined by where the wall is between the domains of 0s and 1s. This has the advantage of both reducing problem size and the number of constraints. The final improvement we've made is in the embedding algorithm. On inspection, our problem graph seemed to have a fully connected core, which is in blue here, plus a few partially connected nodes in green. There exist efficient algorithms for embedding fully connected graphs in the D-Wave Pegasus graph, and it turns out to be quite easy to modify those algorithms to reduce the embedding search space and include those partially connected nodes. This graph shows how the overall embedding size was reduced. So the y-axis is the number of physical qubits required by embedding, and the x-axis is the problem size. And you can see here that as we go from the original embedding in blue, adding the variable reformulation, the main wall encoding, the clique embedding, and so on, the embedding size falls. And eventually we get to a point where we can embed larger problems than before with a much higher success rate, which is shown by the size of the node. The biggest improvement, however, is in terms of time. In this plot, the y-axis is the time taken for the embedding, and the x-axis is again problem size. The solid lines here are the embedding time without the clique embedding algorithm, and the dashed lines are with the algorithm. Actually, we capped the time for this experiment at 100 seconds. Otherwise, this graph would have shot up as before to tens of minutes. You can see here that the scaling of the clique embedding is essentially flat, eventually reaching a 3 or 4 orders of magnitude improvement than the old algorithm, so from 20 minutes to under a second, now comparable with the actual annealing time, which is a huge improvement. So in summary, we investigated the problem of arranging ULDs in an aircraft cargo bay to optimally place the center of gravity. We found that for phase 1, which was the knapsack problem, annealing performs very poorly and classical methods are much better. For phase 2, the key problem was that the embedding failed for large problems, but the time scaling was much better than classically, which was promising. To solve the embedding problem, we've implemented a variable and encoding level reformulation, as well as exploiting the problem graph structure to reduce the embedding time from over 20 minutes to under a second. We're planning to rerun this experiment with the improved embedding algorithm, and we expect to see a huge improvement in the overall annealing solver time, which we hope will also translate to an improvement in the solution quality, especially given the reduction in the annealing size. We're also planning to make the problem more complex. As it is, we made a number of simplifying assumptions, but we're planning to add multiple aircraft and ULD types, which introduces compatibility constraints, disjoint cargo base in the planes, so the calculation of the center of gravity is more complex, different flight schedules, so we can include ULD deadlines, adding and removing ULDs from the pool to reflect, orders coming in and being satisfied. And the aim of all this is to push this setup closer to a production scenario to see how it performs in an end-to-end pipeline. So, thanks for listening. Are there any questions? Yeah, please feel free to unmute yourself and just ask if there are any.
Yeah, hi, I have a question.
Sorry, Daniel, I can't hear you.
Yeah, I have a question.
Can anyone else hear Daniel?
Let me put it. I'll put a headset on.
Okay, it might be from my end then.
Yeah, can you hear me now, Manav?
Sorry about this. How about now?
Yeah, can you hear me?
Okay, yes, I can hear you, Daniel. Sorry about that.
That's great. But thanks very much. It's a great presentation. So I started to put that in the chat. Yeah, I just wanted to know, is this published? Is there anything on the archive to look at? Because some of your techniques seem really powerful, Manav, and it'd be really good to study them.
Thanks, Daniel. Thanks for saying that. So as I said, we're currently performing a more rigorous statistical analysis. So these are just a few preliminary drafts that I cobbled together from the raw data. We've pre-registered. It's it's online pre-registration, and we plan to submit to archive by the end of the year, if not early January next year. So yeah, I'll definitely that's in the pipeline.
Thank you very much. Thank you.
I do have a question. You went through it very fast, maybe I missed it, but why did you pick these annealing schedules that you described in the beginning? And whether what is the impact of the time to solution on this? Have you experimented a bit more on this?
Yes, so the annealing schedules, so the time to solution we calculated was the time between sending off the problem to D-Wave and getting back the results. And the way the time is broken down on the QPU is most of the time is spent actually setting the biases and couplings. And then the annealer performs several hundred sweeps of the annealing. So it goes from S equals 0 to 1 several hundred times and sends back all of those results. And upon examination, that is about half of the total annealing time. So yes, as you see here, the first annealing schedule was about 20 microseconds and the second was about 100. So of course, this is 5 times longer. However, we felt that rather than the total solver time being important, it was the scaling that mattered to us. So if you remember from the times I showed, all of the anneals took about 0.1 seconds with essentially a linear scaling, which was due to the problem size of setting the biases and couplings. So we felt that while choosing a longer reverse annealing schedule does impact solution time, it's essentially a constant overhead, and it doesn't actually affect the scale of brain. And in reference to why we chose these annealing schedules, a literature review told us that there are essentially 2 families of schedules that are being investigated right now, with and without a pause. And we felt that rather than essentially turning this project into a detailed examination of what each of these parameters might mean for the final annealing, we chose to examine just 2 archetypal representatives of these families and relegate a more detailed exploration down the line. The reason with the pause is essentially to let the state spread out a bit more in the solution subspace. And we felt that that might improve the chances of getting an optimal solution. The downside to this is, of course, that might decrease the coherence of the qubits and introduce more errors. So yeah, we just want to compare what effects these 2 had. I hope that answers your question.
Yes, it does. Thank you.
Does anyone else have any more questions? Okay, so I think we're going to end the seminar here. Just want to say thank you to Manav again for presenting this morning. The presentation will be uploaded onto YouTube later on today. And we do have a seminar next week, Tuesday on the 8th of October, and that will be at 4 p.m. So yes, thank you again for everyone joining, and yeah, I will end it here. Thank you again.
Thank you. That's good. Bye.